All right, so these are the linear quantities that we're familiar with. This is just suvat, and then there's force and there's mass. And what we're going to do here is we're going to talk about a little bit about the angular equivalent of that. So angular force is torque, right? And that's the Greek letter tau. The lowercase tau looks just like a T, but this one looks like this. It's kind of like, right, and it's like, right. Anyway, I thought that was funny. But anyway, it's this Greek letter tau like that, and the equivalent of mass is not mass. We actually have to do something called the moment of inertia. These are going to be constructs such that when we get to this equation, right, that see if we can make that appear. There we go. Okay, when we get to this equation, we'll be able to say torque basically F equals angular mass times angular acceleration. Okay. So the first thing we'll do is we'll talk about what torque has to be. Then we'll talk about what this is, and then look at the richness of the problems that could possibly be had if we could solve stuff with this. Okay, so let's hit the right arrow here. The first one is just torque, right? We're going to torque about this a little bit here, right? See, I just can't hear you laughing. Okay, so torque is just a twisting force that can cause an angular acceleration. So let's imagine that we're going to torque this bolt. Okay, we can increase the torque, of course, by either pushing here with more force, right? Or we can actually push farther out. So where you push, and actually even what direction you push, right, is important with this. Okay, so let's look at it, right? This is the actual formula for it. Okay, the torque is R cross F. This is actually something called the vector product. For now, let's just say we're multiplying, but we'll talk about that later in the class. Okay, so that's actually something called vector cross product. Okay, so and let's just do an example of this. Right? We've got a radius, we've got a force. Okay, if it's 0.5 meters and 80 newtons, right, then our torque is just simply RF. And if they're at right angles, it's as simple as this. We just multiply them like that. Okay, so it's 0.5 meters. Okay, times 80 newtons. And so we end up with 40. We don't even have a decimal point. Now we do. Okay, and the units are meter newtons. Little m, big N, like that. Okay. It is the same units as joules, but it's not the same thing as joules. That is, a torque alone, if it doesn't, we don't actually angularly displace this. It doesn't do any work, but it is a twisting force. Okay. Anyway, there we go. Let's do in the next example. We're going to do the mother of all problems. But first, let's look at this. This is actually something called a torque wrench. Whoops, that cue got kind of crazy there. There are two types that I'm familiar with. One has a big shaky needle on it that's basically worthless and points as the more you twist, the farther that needle deflects. This one's got a little dial right here, and you can dial up what torque you want, and then there's a little knob on the end to lock it at that torque. And then if you have to do, like, say, a bunch of these things to 22 foot-pounds, when you reach 22 foot-pounds, this thing goes click, click, and you know that you're at 22 foot-pounds. Which is very, very handy because you can feel that and you can stop right away. Otherwise, you run the risk of twisting off a bolt, which is a truly evil thing to do. Anyway, let's look at where we possibly have a force that's not at right angles. And I think we can all agree that that's not the best way to twist this bolt off. We all understand torque well enough that we know that at right angles is better. But if there is a force that's at an angle like that, okay, that means we've got two components here, right? And this side here is F cos theta, right? This side is F sine theta. This side doesn't matter. This side doesn't create torque, okay? It's this side that creates torque. So the magnitude of the vector cross product is RF sine theta, right? And because it's sine of theta, it's a maximum at 90 degrees. 90 degrees is the maximum value you can get from sine, right? So it's basically, the cross product is the extent to which the radius is at right angles to the force. That's what it really means. And then it also has a direction to it. Okay, in this case, it would be actually out of the page, but we'll deal with that, right? But anyway, this is the real formula as far as the magnitude of the torque goes. Okay, and it's because it's only the perpendicular part that gives rise to it, right? Okay, and we will revisit the vector cross product when we get to magnetism, because there's a lot of right hand rule stuff like that has to do with vector cross product. Okay, so here's an example problem. I'm trying to trick you with this example problem. We've got 24 centimeters, and that's not the trick, that's 0.24 meters, right? Okay, the trick is that 56 degrees is not the angle between R and F. It always has to be an angle that starts on R and ends on F. Okay, so that would be a possible angle. We could use a 90 plus 56, right? We could use 146. We also could use, if we imagine a line out here, we can also use this angle here, right? The 34 degree angle, which is the one I'm inclined to use. Okay, either one of those works, and the reason why, of course, that they work is that if we draw a careful unit circle here, they're supplementary angles, and supplementary angles, here's your 34 degrees and here's your 146, right? Okay, they have the same sign because supplementary angles do have the same sign. Is that right? At least these supplementary angles have the first sign. Luckily I'm not your math teacher. Okay, so we're going to do torque here. Torque is RF sine theta, right? So that's 0.24 meters, and then it's the force is 16 newtons, and then I'm going to go sine of 34 degrees. Is that right? Let me just double check that. I'm so spacey. Let's see. Oh yeah, it definitely is. Okay, so here we go. So 0.24 times 16 times. Checking my mode. I'm in degrees. Okay. Times 16 times sine of 34. And that is 2.147. I guess we only have 2 sig figs, so it's sad that we'd have to say about 2.1 meter newtons. But we'd use this number, or even more than that, right? Okay. And then I think all there is left is, oh no, let's talk a little bit about bike wheels. Okay. Okay, so this is fun, right? This is the chain ring and the, what do they call that? The freewheel or something like that. Okay. And we want to get the most torque on that back tire. Well, this thing's exerting a force. Basically, this chain is under tension. This one's not under tension. At least not much tension, just enough to keep it from banging around, right? Okay, so in order to get the most torque on the back wheel, the force, you'd want to exert the force at the biggest R, right? So the biggest wheel gives us the most torque, and that's because torque is RF, and if the tension in the chain is the same, to get the biggest torque, you'd want the biggest radius, right? So definitely the big ring would be the one you'd want to use there, right? And then on the front of these front two chain rings, let's look at this. For these guys, the torque is the same. So RF for the big ring equals RF for the small rings. If the many gears share the same axis, they all have the same torque, right? And so RF, R big, right? F, so this guy's a big radius. That means it's a small force. If this is a small radius, it's a big force, right? So the small chain ring actually exerts the most force. So we all understand if you want the most torque, right, then you would use the biggest force, which would be the smallest chain ring and the biggest gear in the back, right? So this is if you're climbing up a hill, right? Small chain ring on the front, big one in the back, cruising, right? Street cruising. And then, heading down a steep hill, right, we would go big chain ring, and the difference was, of course, that this would give us a lot of speed. All right. In the next few videos, we'll solve a bunch of torque problems here.